I'm also going to record it so I can post it for the people who did not come. Okay, so we're going to talk here about the Doppler effect a little bit, review it. Again, last week you had videos in which you were supposed to, and there was the question in which you were supposed to demonstrate to me your knowledge of the Doppler effect. So again, waves are created by a source, right? Again, waves are not mass. It's not like me throwing a tennis ball. A wave is a disturbance that moves out from the source because the source is causing a disruption in a medium. And that medium can be anything from air to water to lots of different things can carry waves. But it becomes more interesting when the source is moving, right? We've all tossed a pebble into a pond and it creates waves, right? Waves move out in concentric circles from where we threw the pebble into the water, and all the circles are the same distance from one another, and they get progressively larger, right? And so that's what happens when you have something creating waves and is stationary. But when the source is moving, or as is a little more complicated, when the receiver is moving, then the waves get a little bit changed. So here we have this picture on the screen, which is supposed to represent an object making waves. So that red dot you can imagine as a person in a swimming pool, just kind of bouncing up and down and making waves. And again, you can make waves, you can make a single wave, or what we more often look at is something that's creating a wave over and over again in the same way. So someone who's bouncing up and down in the pool, say 5 times a second, they're going to make these waves that are going to go out in all directions around them. But if they're bouncing up and down and wading through the pool, then we're going to get this result, okay? So this red arrow indicates that the red dot is moving to the right. So as they move to the right, they make a wave, and then they chase after the wave and make another wave. And so those waves are scrunched together, right? There's less distance between them because the source followed the wave. And at the same time, behind them, they make a wave, and then they run away before they make another wave. So those waves are stretched out. They're longer than they would be. And the effect on wavelength is interesting, but that's not what we can detect easily with sound. What we can detect easily with sound is the frequency, because that's the pitch, what we hear. But they're related, right? They're related via the wave equation, which, you know, I speechified back in chapter 11 about how important this equation was going to be, not only for that chapter, but for subsequent chapters, including this one, chapter 12. So again, this is the wave equation. The velocity of the wave equals the frequency of the wave times the wavelength, right? The wavelength is how long it is in meters. The frequency is the inverse of time, right? If we complete 5 cycles in a second, we have a frequency of 5. That means each cycle takes 1/5 of a second. So it's 1 over seconds. So if you multiply those two together, you end up with meters in the numerator, seconds in the denominator. That's meters per second. That's the velocity. Okay, that's just a review of the wave equation. But what we need to remember about the wave equation is that waves velocity does not depend on how fast you bounce up and down. A wave's velocity depends only on the material that you're in. So whether you're moving or not, that's not going to change the material you're in. So the velocity of the wave is going to stay constant because the material you're in is staying the same. So if we have a moving source like this and the waves get shorter, when the waves get shorter and lambda gets smaller, then the frequency is going to have to get bigger to compensate, right? Because the product of these has to equal a constant. So they're inversely related. When one goes down, the other goes up. So here we have the discussion of the source moving towards you or the receiver moving toward the source. Both will cause the same result. The waves will effectively be scrunched together. The wavelength will get shorter and the frequency will therefore get higher. On the other hand, behind, we have the opposite situation. The wavelength is getting longer and therefore the frequency is going down. Okay, so when you're moving toward the source, the frequency goes up. When you're moving away from the source, the frequency goes down. Or when the source is moving towards you, the frequency goes up. When the source is moving away from you, the frequency goes down. But you got to be careful with that moving toward and moving away, because what if both the source and the receiver are moving? Are they moving toward each other, away from each other? What if they're both moving the same direction, but the back guy's moving faster? You know, it just depends. So that's where we're going to go to an actual situation and see how we go about solving the problem. So again, we get to look at Mr. Rassi's incredibly beautiful art, where he drew this picture, and I forget, I think this might have been the one that I actually gave you to do one of the weeks. I ended up giving you 2 of these, but so we have 5 things, right? We've got the police car, which is actually making the sound. We have a truck, a bicycle, a car, and a pedestrian. And the question is, who hears the frequency of the siren the highest and who hears it the lowest? And so we're going to go through this progression and discuss what each of these is going to be. So again, it's difficult because the source is moving and many of the receivers are moving too. And so the way we're going to fix this confusion is we're going to put everything in the perspective of the police car. Okay, the police car is the source, and so that's what we really care about. Are you moving toward the source or away from the source relative to the source? So we're going to shift our frame of reference. Right now, our frame of reference is the ground, which is indicated by the fact the pedestrian has a speed of 0. We're going to shift ourselves into the frame of reference of the police car. That way we can see what is moving toward or away from the police car in terms of the actual source of the sound. Again, if we think about this, right, when you're driving down the road and you see a tree up ahead, you can either think of it as I'm moving toward the tree at 60 miles an hour, or you can think of it as the tree's moving toward me at 60 miles an hour. Both of those are valid descriptions depending on your frame of reference. So we're going to go into the police car's frame of reference, and we do that by canceling out his motion. So if his motion is 30 miles per hour to the right, we're going to cancel that out by adding a vector of 30 miles per hour to the left. So 30 to the right plus 30 to the left, that ends up giving the police van a grand velocity of 0. Okay, that's fine. That's easy for the policeman, but now we need to do that to everybody else. Okay, so the truck was going 20 to the left. We add another 30 to the left, and now the truck is going 50 to the left. Okay, the bicycle was going 5. We add another 30. Now the bicycle is going 35 to the left. And those 2 vectors are not the same length. So we're going to try again. They were the same length. They weren't supposed to be the same length. Okay, so the truck's going 50 to the left relative to the police car. The bicycle's going 35 to the left relative to the police car. The car is going 20 to the right. So when we add 30 to the left, the car is going to end up going 10 to the left. And the pedestrian, who is going 0, is going to end up going 30 to the left. Now, I've been describing these as left and right, and that's okay for now. But what really matters is whether they are moving toward the police car or away from the police car. So now we're going to go back and we're going to put in signs, right? We're going to put in a sign, a positive sign if it's moving toward the police car, and a negative sign if it's moving away from the police car. And of course, the police car has a 0, which is neither positive nor negative. So now we look at our 5 numbers, and we put them in order from largest to smallest, because the truck is moving toward the police car at 50 miles an hour. So he's going to hear a large shift up, right? The faster you're going, the larger that shift is going to be. The bicycle is moving toward as well, but it's moving a little slower, so the shift is going to be a little bit smaller. They're both going to hear it higher, right? They're going to hear a higher pitch than normal, but it's going to be a greater amount higher for the truck and a lesser amount higher for the bicycle. And then finally, we're going to have the police car, who's going to hear it normal, right? He's not moving toward or away. We have the car now, who's moving away at 10. So he's going to hear it lower than normal, right? And then the pedestrian, who's moving away the fastest, which is confusing, right? Whoops. Confusing because the pedestrian's actually sitting still, but relative to the police car, he's moving backwards the fastest because the police car's already passed him and he's moving away at 30. So we put these in order from largest to fastest moving toward to fastest moving away. And that gives us the order of frequency from highest to lowest. So now we just have to translate that into the actual object. The truck here's at the highest, and then the bicycle, and then the police car here's at normal, the car here's at lower, and the pedestrian here's at the lowest.